Okay, well, welcome everyone to the first talk of TCS Plus for the semester. We're very happy to have Will Hoza here from ET Austin talk to us about fooling constant depth threshold circuits. Now, before we begin, let me just say that in 2 weeks from now, we'll have another talk by Steve Haneke. He'll talk about a theory of universal learning. And just a shout out to the rest of the organizers, which include Clement Knan and India Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, and Thomas Vidik. But yeah, other than that, please feel free to unmute yourself and encourage to keep the camera on so that Will has some visual feedback. And yeah, if there's any questions, you can use the chat. I can also try to interrupt. And I think, oh, one more thing, that Will is in Texas, so there may be a sudden power outage, in which case we'll have to postpone the talk, but hopefully it holds through. Okay, that's all. Well, take it away, Will.
Sure. Okay, thanks for the introduction. And thanks to all the organizers for hosting this and inviting me, and thanks to all of you for coming. So today I'm going to present joint work with Puya Hatami, Avishai Tal, and Roy Tell. So to motivate this work, let me try to connect it to P versus NP. So the standard approach that people hope and dream that maybe someday we'll use to prove P not equal to NP is to prove a circuit size lower bound. Right? Non-explicitly, we know just by counting arguments that there exists a function with exponential circuit complexity. And if only we could get our hands on one, right? If we could prove that there's some language in NP that has super polynomial circuit complexity, that would imply P doesn't equal NP. But unfortunately, the state of the art right now is very far from that goal. The best lower bounds for problems in NP for circuit size are linear. It's maybe 3 times n or 5 times n, depending on exactly how you formulate the question. And so in order to make progress, researchers have turned to more restricted classes of circuits, restricted circuit models. And then if we can at least prove lower bounds for these simpler circuit classes, then maybe that's some kind of progress toward eventually someday proving P not equal to NP. So one example of a restricted circuit class would be AC0, constant depth circuits. And these circuits are understood quite well. Right. Since the 80s, we've known exponential size lower bounds, even for just simple functions like the parity function. Okay. And we also have good lower bounds in like a qualitative sense. The lower bounds from the 80s were already average case lower bounds, saying that an AC0 circuit can't even compute the parity function on average, on a good fraction of inputs. And the average case lower bounds were also refined a little more recently. And another qualitatively better type of lower bound is a pseudorandom generator. And there's been quite a lot of work developing very good pseudorandom generators for AC0, including even in the last couple of years. Okay, so we understand AC0 quite well. So maybe now it's time to move on and consider a more challenging class. So this talk is going to be about TC0, which stands for threshold circuits. So threshold circuits are based on linear threshold functions. An LTF is otherwise known as a half space. It's a Boolean function on n bits, and it takes a weighted sum of its inputs and compares it to some threshold theta. Okay, or equivalently, it takes the inner product of its input x with some weight vector w and checks whether that's at least theta. And this weight vector w is just arbitrary real numbers. Okay, so this generalizes and or gates. It also includes things like the simple majority function and lots of others. An LTF circuit is what it sounds like. It's a circuit where the gates are arbitrary LTFs. So you could think of this as being like a really crude mathematical model of a brain, right? Because one individual LTF is sort of similar to an individual neuron in a neural network. Now, the complexity measure that we're going to consider is the number of wires in the circuit. So that'll be what we mean by the size of the circuit. We're counting wires. We're not counting gates. So TC0 is constant depth polynomial size threshold circuits, LTF circuits. So it's analogous to AC0. We just changed what type of gates are allowed. And of course, these gates have unbounded fan-in, just like AC0. So the state of the art for lower bounds for TC0 is not nearly as good as for AC0, but still something is known. For TC0, we have slightly superlinear size lower bounds. In particular, Impagliazzo, Paturi, and Sachs showed, now it's been almost 30 years, they showed that parity cannot be computed by a depth D LTF circuit unless it has at least like n to the 1 plus delta wires, where delta is some tiny positive number that decays exponentially with the depth D that we're fighting against. Okay, so it would be great to improve this lower bound quantitatively, to get lower bounds against larger LTF circuits. But in this work, we're instead focusing on these more qualitative types of improvements, a qualitatively better lower bound. So an average case version of this statement was proven by Chen, Santhanam, and Srinivasan a few years ago. And this work is about pseudorandom generators for TC0. So prior to this work, there was no non-trivial pseudorandom generator known for threshold circuits. There was no pseudorandom generator that corresponds to this lower bound. And so that's where we come in. So a pseudorandom generator, to remind you, is a function that stretches a short, truly random seed out to a long pseudorandom n-bit string. And to make this pseudorandomness condition precise, we consider some class of test functions C. So in our case, these test functions are going to be threshold circuits. And the requirement is that for any circuit in the class, the acceptance probability of the circuit is basically the same, whether you plug in a truly random input or you plug in a pseudorandom input that we got from the generator. Okay. So this value epsilon, the additive error between these acceptance probabilities, is called the error of the pseudorandom generator. And then the number of truly random bits that the generator uses is called the seed length of the generator. So ideally, we'd like the error and the seed length to be as small as possible. You can think of a pseudorandom generator construction as being like a particularly strong type of lower bound against this circuit class. Intuitively, this condition is saying that like this circuit class C cannot comprehend at all what is going, what this generator is doing. It doesn't understand its operations in the slightest. As far as the circuit class can tell, what the generator is doing just looks like random gibberish. Okay, so here's our main theorem. We construct an explicit pseudorandom generator for LTF circuits. And it's in this same regime of parameters that matches the state-of-the-art lower bounds, where we're considering size n to the 1 plus delta circuits, where delta is just this tiny positive number that decays exponentially with D. Okay. And just as a reminder, when I say size, I'm talking about the number of wires. Now, the seed length of our pseudorandom generator is n to the 1 minus delta. So we're stretching n to the 1 minus delta bits out to n bits. And then it has exponentially small error, 2 to the minus n to the delta. So the seed length might be a little bit disappointing, right? It's only like just barely non-trivial. It's just barely below n bits, which would be trivial. But our excuse for that is that any significant improvement to these parameters would imply new lower bounds, which of course doesn't necessarily mean it's impossible. I mean, I hope one of you will see this and figure out how to improve it and prove new lower bounds. But hopefully that counts as something of an excuse. So that's the main theorem. I hope it's clear. So stop me if you have any questions about what the theorem is saying or why we should care about it. But otherwise, I'm going to get started with the proof.
I have a question, William.
Yeah.
So you have a pretty small error. Is this a consequence of your approach, or do you need to do extra work to get this good dependence on the error? Thank you.
Yeah, that's a good question. You're right. I'm glad you appreciate. The error is low, it's like you said, a consequence of our approach. So it was actually like there was a bottleneck at intermediate stages where we couldn't get anything unless we could get it with exponentially small error. So it didn't take extra work to get exponentially small error. That sort of like that it was somehow necessary for the approach to work, that we had to make everything have exponentially small error. And I'll point out why later in the talk, although it's a little bit subtle.
I see. Thank you.
Mm-hmm.
So I have another question. Is it specifically for the parity function? Is it believed that you can't do it with threshold circuits like this?
Good question. So there's an upper bound for the parity function that basically matches this lower bound. So the parity function is not, if you're looking for a really hard function for LTF circuits, if you're hoping to improve this lower bound, you're going to need to be more creative than just considering the parity function. More generally, like any symmetric function can be computed by polynomial size depth 2 LTF circuits. So does that answer your question?
Yeah, thanks.
Great. Okay, great. All right, so let me then get started telling you about how this pseudorandom generator works. So the pseudorandom generator is based on pseudorandom restrictions. So a restriction is a string over this 3-symbol alphabet, 0, 1, star. Intuitively, a star means that variable is still alive. It hasn't yet been assigned a value. We're still not sure whether it's going to be a 0 or a 1. And we're going to consider p regular restrictions. This value p is the star probability. Okay, so each coordinate is star with probability p, and otherwise it's 0 or 1 independently. I mean, 0 or 1 with equal probability. And the coordinates here are not necessarily independent. So we're not talking about truly random restrictions. We're going to be considering, somewhat pseudo-random restrictions, but the star probability will be p. That's the important thing. So we're just talking about the marginal distribution. So our pseudorandom generator is constructed using this general framework introduced by Itai and Vigderson. And so they came up with this sort of general recipe for constructing a pseudorandom generator that's pretty flexible. It's had a lot of success. So the first ingredient for their framework is a pseudorandom restriction where the star set can be sampled efficiently using a short seed. And then the second ingredient is that we need that with high probability, when you hit the circuit with this restriction, the circuit simplifies in the sense that we can fool the restricted circuit. So with high probability, we land in some class C simple for which we can design a pseudorandom generator. And so I guess that pseudorandom generator is the second ingredient of this framework. And so if you have these two ingredients, then there's a simple like recursive trick. I mean, let me not explain in detail exactly how it works, but Itai and Vigderson noticed there's a sort of a simple trick that lets you combine these two ingredients and get a pseudorandom generator for the original circuit class that we're interested in. Okay, so without going into details, I just want to emphasize one thing, which is that in this framework, for this to make sense, this event that the circuit simplifies, the failure probability needs to be smaller than p, the star probability, and that's going to be important for us. Okay, so just to summarize what we need to do, we need to show two things. First, we need to show that LTF circuits simplify when you hit them with a suitable pseudorandom restriction, and then second, we need to fool the simplified model. So let's start with the first thing. Let's show that LTF circuits simplify. So we'd better first consider just an individual gate of this LTF circuit. So one linear threshold function. Our hope is that when we hit this LTF with a restriction, then it will simplify in the sense that it will become extremely biased. So what I mean by that is that we say some Boolean function is epsilon close to a constant if there's some constant b such that the function outputs B with probability at least 1 minus epsilon when you plug in a random input. Okay, so we're hoping that after we hit this LTF with a restriction, it will become close to a constant. Okay, so to see why that would happen, let's consider the simple majority function. Okay, so if we do a random restriction, intuitively, I mean, we should expect that there are about equal numbers of zeros and ones, but it would be kind of surprising if there were exactly the same number of zeros as ones, right? It's more likely that there's going to be some gap. There will be either a few more ones than zeros or else a few more zeros than ones. In this case, we have a few more ones than zeros, okay? And the point is that once there's that gap that's been established, there are only a few stars remaining. And so the gap, we can expect that the gap will probably be big enough that now it would be very difficult for these stars to overcome that gap, you know, and swing things the other direction and cause the majority to output the other value. Okay, so we can expect with decent probability that the function, the restricted function, will be extremely biased. Okay, so let's do that quantitatively. So let's do a truly random restriction that leaves Pn variables alive. A P fraction of variables are alive. Okay, then I claim that the restricted majority function will be epsilon close to a constant, except with failure probability square root P log 1 over epsilon. Okay. And so the proof is just, you know, formalizing the intuition that I said on the previous slide. First, we make an anti-concentration statement. So this is where we say, it would be surprising if the restriction had exactly half zeros and half ones, okay? The probability that the number of zeros is within delta of the number of ones is only like delta over square root n. Okay, we expect there to be a size delta gap between the number of zeros versus the number of ones. Okay, and the reason is simply just by considering like the maximum binomial coefficient, right? Like n choose n over 2. All right. Okay, and so then assuming that went well, assuming that we've established that delta size gap between the number of zeros and number of ones, then when we pick a random input to the restricted function, it would be surprising if that input managed to overcome that gap, right? If the number of zeros, if the difference between the number of zeros and ones in that input were at least delta. Okay, and this is just a standard concentration bound now, like Chernoff bound or Hoeffding's inequality. Okay. So if you pick the right value of delta, I mean, there's a little bit of a calculation to do here, but if you pick the right value of delta, then these two failure probabilities come out to square root P log 1 over epsilon and epsilon, just as I claimed. So that's the analysis of just the simple unweighted majority function. Since we want to handle general LTF circuits, we do need to consider general LTFs with weights. So let me just quote a result here that's a generalization of what I had on the previous slide, basically. So Chen, Santhanam, and Srinivasan showed that when you do a truly random p-regular restriction, then an LTF will become epsilon close to a constant, except with this failure probability. That's like, qualitatively, it's similar to what was on the previous slide. It's like p to some small number times log 1 over epsilon. I mean, I should mention that actually, in the paper, we need a more technical variant of this statement for our actual pseudorandom generator. I mean, for one thing, we need like a de-randomized version of this statement. And there are some other technicalities. But for today, let's ignore these technicalities and just consider, this sort of phenomenon, which is that LTFs become close to a constant when you hit them with a random restriction. Okay, so let's return now to the entire LTF circuit. We'd like to show that the circuit simplifies as a whole when we hit it with a pseudorandom restriction. So the idea is we're going to focus on this bottom layer, the gates at the very bottom of the circuit. and we're going to try to collapse it. So we're hoping that the depth will effectively decrease by 1. And the intuition is, I mean, most of these gates at the bottom are going to become close to constants. That's what we were just analyzing. And so if it becomes close to a constant, intuitively, we should be able to just replace it with that constant. And that hardly affects the computation, the behavior of this circuit. Okay, so the main difficulty with this approach is just the fact that some of the gates are not going to become extremely biased. We have to actually deal with that failure scenario because the failure probability isn't low enough for us, right? I mean, even for an individual gate, the failure probability that we saw, like for the majority function, it was like square root p, okay? And like I mentioned a few slides ago, we actually need our overall failure probability to be much smaller than p. So that's a problem for us, even just if there's one gate at the bottom that we're trying to analyze. So just, I mean, what this means is that we have to accept the fact that some of these gates won't become extremely biased, and we have to do something else to deal with those. So the key to handling, these failure scenarios is a carefully engineered choice of our C simple, the model to which we're trying to claim these circuits simplify when we hit it with a pseudorandom restriction. So the model that we'll consider is this like hybrid decision tree model. It's a model that combines decision trees with LTFs. So it's a decision tree where it can query variables like a normal decision tree, but also a node can query an arbitrary LTF. So it can apply some LTF to the input and branch based on the value of that LTF. And then at the leaves of this decision tree, we actually have entire LTF circuits. So these are what ultimately give the output of the decision tree. So the final step of this decision tree computation is to run some LTF circuit on the input. Okay, so a similar kind of model was was studied by Chen, Santhanam, and Srinivasan. And so this is what we're going to claim. This is going to be our simplification statement. We're going to say if you start with an LTF circuit and you hit it with a pseudorandom restriction, then with high probability, you'll get one of these LTF decision trees where the circuits at the leaves are shallower than the circuit that we started with. So that's the sense in which we're making progress. We're still talking about decreasing the depth of the circuit, but the penalty we pay is that we've increased the number of circuits because there are now all these queries above them in this decision tree. Okay, so here's the depth reduction lemma more precisely. So we start with some depth D circuit and we hit it with a p regular restriction. And it needs to be a particular kind of pseudorandom restriction, but never mind. And the lemma says with high probability, the restricted function can be computed, well, okay, it can be approximated. It can be computed by some LTF decision tree where the circuits at the leaves now are depth D-1 LTF circuits. Okay, so that's the sense in which we've made progress. We went down from depth D to depth D-1. And then the penalty we pay is that we need to do a bunch of queries. We're going to do variable queries and LTF queries. Okay. And the number of variable queries here is like p to the 7/6 times w. Okay, so the way to think about this, the value p, you should think of p as being like 1 over some small polynomial in n. Okay, and then remember we're thinking of w, the number of wires in the circuit. We're thinking of that as being like slightly superlinear, so it's very close to n. So what that means is that p to the 7/6 times w brings us substantially below p times n. Right? I mean, the number 7/6, the specific number isn't very important. It's just 7/6 is bigger than 1. That's the important thing. Okay, p times n would be like the baseline. Okay, because when we do this, we're doing a p regular restriction, so that's going to leave pn variables alive. So a depth pn decision tree would be maximal depth. That would be an all-powerful model that could compute any function. So what we're claiming here is that it's slightly sub-maximal depth. So this is not an all-powerful model, and we really are making some non-trivial claim, which is good because ultimately we're going to need to fool these things. We need to design a pseudorandom generator for them. Okay, so So the 7/6 means we're staying ahead of the trivial, all-powerful maximal depth model. Okay. And then, all right, there are also a few LTF queries, but there aren't so many of them. So let me tell you how we prove this lemma. The general technique, and this goes back to work of Hastad's, is to say whenever some bad event occurs, some undesirable, unfortunate event, then we'll just query whoever's responsible for the bad event. Okay, use our query power to query the variables or LTFs that are responsible. That way, beneath those queries, at the circuits that go beneath those queries, we can plug in the query values. And so that means that the problematic parts of the circuit, these things where something went wrong, they effectively disappear because they've had values plugged in for them. Okay, so let me show you how this works. So the proof actually, unfortunately, involves a little bit of casework. We need to split the gates into heavy gates versus light gates based on the fan-in. And then we also need to split the variables into heavy variables versus light variables based on the fan-out. So maybe the main case of the proof is when we ignore everything except heavy gates and light variables. So we pretend that's all there is. Okay, and let's let M be the fan-in of the gates. And for simplicity, let's just pretend it's the same M for all gates. Okay, so then the theorem we saw before about analyzing a single LTF under a random restriction tells us that each gate is going to become extremely biased, except with this moderate failure probability, p to some small power. In fact, it turns out to be roughly p to the 1/3. And so the challenge, like I was saying earlier, is that we need to deal with the gates that did not become extremely biased. In other words, the gates that remained somewhat balanced. Right now, in expectation, the number of these troublesome, somewhat balanced gates is like p to the 1/3 times the number of gates. And the number of gates is certainly at most W over M, just because W is the total number of wires, and each gate has fan-in M. And so the way that we deal with those is, well, we do one of two things. If the total number of gates is small, then okay, it's in our budget to just query all of these somewhat balanced gates. Remember, we could do a few LTF queries. But otherwise, if there are a lot of gates, the sort of the main case, then instead we query the variables that feed into the somewhat balanced gates, which also gets rid of them, right? If we query all the variables feeding into them, they'll disappear. Okay, so we just need to count the number of queries to make sure we didn't go over budget. Right now, I said query the variables feeding into the somewhat balanced gates, but of course we only need to query the star variables, right? If it was assigned a value, then there's no need to query it because its value is just hard-coded into the entire tree. So we need to query the ones that are still alive. So we would expect for a single gate, the number of stars feeding into it, that should be like p times m. Plus some, additive error. So that means that summing up, in expectation, the number of variable queries we do is like p times m plus this, log term, times the number of somewhat balanced gates, which is this, up here. And if you plug that in and just do a little bit of arithmetic, it comes out to p to the 7/6 times w. So that's exactly within our budget. Okay, one challenge here is that calculation was just, we were calculating the expected number of variable queries, but we do actually, we need to show that with high probability, we only do this number of variable queries, like, except with exponentially small failure probability. And so without going into detail, that the way that we do that is we use something called the Reed-K-Chernoff bound, which is a very cool concentration bound. And this is the part of the proof where we're using our assumption that the variables have low fan out, light variables. Okay, so I'll let you look at the paper if you're curious about exactly how that argument works. But let me move on now and talk about another case of the proof, which is light gates and light variables. Okay, so everybody's low degree now. Low fan in, low fan out. Here, we take a different approach. This time, we're not even going to hope that the gates become extremely biased. I mean, they might, but never mind that. Instead, we're going to hope that after the restriction, each gate, we're going to hope that it has fan in only 1 or 0. We're going to hope that enough of its variables got assigned values that now there's only 1 star or 0 stars feeding into it. Okay. In that case, I mean, a Boolean function on 1 bit is just it's either a constant or a literal. So once again, this allows us to decrease the depth of the circuit because we can eliminate this gate and just replace it with a constant or a literal. Okay, so that if we're hoping for this to happen, we're hoping that the fan-in goes down to 0 or 1, then the troublesome case that we need to be worried about is 2 variables that feed into the same light gate. Right? So let's call that a connected pair. And the bad case for us is when both of those variables survive. They're both star. And so what we do in that scenario is, of course, what we always do, which is query whoever's responsible, right? We query the variables that are in the connected pairs where both survive. Those are the variables that, those are the variables where something went wrong. So we just query them. Okay, so how many queries is that? Well, for one connected pair, the probability that both variables survive is p squared. And the number of connected pairs, to count that, let's consider each wire. Okay, how many connected pairs can one wire participate in? Since the gates have low fan-in, each wire can only participate in a few connected pairs. And so you can see that these numbers, are exactly chosen so that this comes out to p to the 7/6 times w. It exactly fits within our budget. Once again, that calculation was just for the expected number of queries, and really to complete the proof, we need to prove that this happens with high probability. We need to do a concentration argument. In this case, the concentration argument, I mean, it's based on, this is like a sparse graph. Everybody's low degree. And so basically that means that, we can find like a ton of gates, a ton of these light gates that read disjoint sets of variables. And so then we have like independent events, and we can start applying standard concentration bounds for independent events. That's the intuition. Again, you can see the paper for details, but. Okay, and then the final case is the heavy variables, which we've ignored so far. So these are the variables with high fan out. Here, actually, this is the simplest case of all. The way that we deal with heavy variables is we just query all of them. We just consider all of them to be, an unfortunate situation. And because of the way the parameter has been chosen, the number of heavy variables is at most p to the 7/6 times w, just because w is the total number of wires. And so again, this, we have the budget to do this. So that's the idea. That's the idea of this depth reduction lemma. That's the sketch of the proof. So what we just showed, by those arguments, or at least sketched, is that when you take a depth D circuit and you hit it with a pseudorandom restriction, you can expect to get an LTF decision tree with depth D-1 circuits at the leaves. Are there any questions about that? Feel free to stop me. Okay. So then at this point, what we'd like to do, of course, is iterate the process. We'd like to continue simplifying this circuit. We need to get from depth D-1 down to depth D-2. The trouble, though, I mean, with this statement is that we started with one type of thing, a circuit, and we ended with a different type of thing, a decision tree. So it doesn't quite make sense to iterate the process from here. So what we'd like is a statement that says if you start with a decision tree, an LTF decision tree, and then you hit it with a random restriction, we'd like to be able to claim that you get another decision tree, the same sort of thing, but the depth parameter has improved, the depth of the circuits at the leaves, that is. So that's what this next lemma says. So this is like a depth reduction lemma a circuit depth reduction lemma for these LTF decision trees. It says we start with an LTF decision tree T, where the circuits at the leaves have depth D. And then we hit it with a certain type of pseudorandom p-regular restriction. Then with high probability, we get another LTF decision tree where this time the leaves are labeled with depth D-1 circuits. And okay, again, we pay this penalty, which is that we have to do these variable queries and also a few LTF queries. Okay, so for the most part, the proof of this lemma is pretty straightforward. For the most part, we're doing sort of the natural thing, right? We start with this decision tree with circuits at the leaves. And so we already know that each leaf individually, when we hit it with restriction, will become an LTF decision tree with shallower circuits at the leaves. So we can just consider each circuit individually and then merge the decision trees. Okay, that's basically the proof strategy. So let me just tell you about one step of this proof that I think is maybe the most interesting, which is where a little bit of subtlety arises. So maybe the key step of the proof is where we're bounding the error of this process. And so we're talking about error both with respect to, there are two types of errors that can occur basically in this whole process. One is that we get a bad restriction. And the other is that we get a bad input, because remember, we've replaced extremely biased gates with constants. And when we did that replacement, I mean, that means that some inputs are bad because some inputs are going to be inputs where the gate outputs the other value and the replacement wasn't valid. Okay, so we consider the probability of error, either type of error with respect to this restriction, a random restriction and a random input. We can write this probability of error by summing over all leaves of the decision tree that we started with, T. So then we have the contribution from one leaf is like the probability that that's the leaf we reach, and something goes wrong in the process of replacing that circuit with a decision tree. Okay, so there's an error at that leaf. Okay, now the probability of error at that leaf, that's something we can handle. That just comes from the previous depth reduction lemma. We can bound that by epsilon. But the danger, the thing that we should be a little bit worried about is that these events are not necessarily independent. Reaching a leaf is not necessarily independent from something going wrong at that leaf. And the reason for that is the LTF queries. Okay. So, I mean, how do you reach a leaf? What causes you to reach some leaf? Basically, it means that if you consider the path along that leaf, there were a bunch of variable queries along that path, and there were a bunch of LTF queries. So we can let vars sub L be the event that our input is consistent with all the variable queries, and LTFs sub L be the event that our input is consistent with all those LTF queries, that bring us to L. Then this event of reaching L is the same as the conjunction, the event that vars sub L happens and LTF sub L happens. And these LTFs cause trouble because remember, each LTF query looks at all the inputs, right? And so we should be worried that maybe these LTF queries tend to bring us to one of the leaves where something went wrong, right? Maybe these LTF queries skew the distribution so that the error probability at some leaf, at the leaf that we've reached, like conditioned on reaching that leaf, the error probability has blown up a bunch. And so the way we deal with that is a very simple trick. I think it's kind of satisfying, which is that we say, well, look, the probability of this event is at most the same sum where we just ignore the LTF condition. Just sum over the probability that the variable queries are at least consistent with that leaf and some error occurs at that leaf. Okay. This is helpful to us because these two events without loss of generality are independent. Okay, because the circuit at that leaf without loss of generality, it ignores the variables that were queried to get to that circuit. That circuit, it doesn't need to look at those various variables anymore because after all, the values can just be plugged in. So these events are independent. And so, now we can bound this, this quantity we can bound by just, some little epsilon prime from the previous depth reduction lemma. And so we're left with the sum of the probabilities of these events vars sub L, or in other words, the expected number of leaves such that we're consistent with all the variable queries to those leaves. Okay, and it's not too hard to convince yourself that, I mean, the only reason there are multiple leaves is these LTF queries that, introduce this ambiguity. And so the number of possible leaves is at most 2 to the number of LTF queries. So this step right here, this is really why it's important that we keep the number of LTF queries to a minimum. Okay, and this is to answer a question earlier. This is why actually it was important for us that the depth reduction lemma has extremely small error, like exponentially small failure probability. It's because actually in each iteration, we blow up the error probability by this quite large value. In each iteration, when we go from one depth to the next, the error kind of explodes by exponentially in the number of LTF queries. So this is the bottleneck in the proof, this step right here, this blow up of 2 to the number of LTF queries. This is the bottleneck that it gives us our final bounds for our pseudorandom generator. This is why we can only handle slightly superlinear size LTF circuits. So I figured, I should probably show this reasoning in the presentation. All right, so that's all I wanted to say about that. So that's the depth reduction lemma for these LTF decision trees. So now, now we can iterate the process because now we have this lemma that applies to these decision trees. And so as a whole, how the process goes now is, right, we start with some LTF circuit and we hit it with a random restriction and we get a decision tree with shallower circuits. And then we hit that with another random restriction and we get another decision tree with even shallower circuits. And we do this over and over and over again, like d-1 times. And eventually, the depth at the leaves, the depth of these circuits at the leaves has gone down to 1. Or in other words, we're just talking about now an LTF decision tree with individual LTFs at the leaves. So this is our overall simplification statement for LTF circuits. It says when you hit an LTF circuit with a random restriction with high probability, you get an LTF decision tree where the leaves are labeled with individual LTFs. And then the penalty we pay is these queries. So the number of variable queries is once again p to the 1 plus some tiny positive number times w. And then there are a few LTF queries. As you can see, when we iterate the process, this tiny number gets really tiny. And once again, that's just, if you go through the arithmetic, it's because of that exponential blow up in the error. But it's still something positive, right? It's p to the 1 plus something. And then, right, okay, we actually need it to be like a pseudorandom restriction. We need to be able to efficiently sample the set of stars of this restriction. So are there any questions about this simplification phenomenon?
Hi, I have a question.
Yeah.
So you said you wanted this p to the whatever w to be much less than pn. Is that not also a bottleneck?
Yeah. So absolutely. Yeah, I meant, so you're absolutely definitely true, right? So looking at this statement, it's probably clear where the bottleneck is, right? We need w to be only slightly smaller than n because otherwise this would be maximal depth. What I meant, yeah, that's a fair objection. What I meant is, that exponential blow up in the error that was on the previous slides, that's like the underlying phenomenon that causes you to get this 40 to the minus d showing up here.
Thank you.
Yeah, good question. But yeah, that's right. So since this is only 1 plus something tiny, that means that for us to be saying anything, for this statement to be meaningful, w needs to be at most n to the 1 plus something tiny. Oh, right. I should mention that in Chen, Santhanam, and Srinivasan's work, they have a sort of they phrase it differently, but their results are a little bit similar to this. So this can be understood as like a de-randomized and strengthened version of some of their analysis. Okay, so at this point, we've shown that LTF circuits simplify. I mean, simplify in one sense. I mean, the model that we ended up with is kind of more complicated than the model we started with from a human perspective, but hopefully it's simpler in the sense that we can fool it. That's really what matters. That's the standard for simplicity, is that we just need to be able to design a pseudorandom generator now for this simplified model. So that's what we're going to do next. So this mainly amounts to designing a pseudorandom generator for polytopes, which is like AND of LTFs, an intersection of half spaces. Okay, so we design a new pseudorandom generator for this model, like an intersection of S many LTFs. And it has this seed length that's like roughly square root n times S plus log 1 over epsilon. Okay, so this model, polytopes, it's been studied before. There have been a few prior pseudorandom generators for polytopes. And the thing I just want to emphasize is that our pseudorandom generator has better dependence on epsilon. You'll notice that we can handle like a really, really small error, like 2 to the minus n to the 0.99, and our seed length is still non-trivial. Okay, these other pseudorandom generators, I mean, might have better seed length for moderate, much better seed length for moderate error. But for our work, I mean, really, we're interested in this slightly non-trivial seed length regime. So for us, this is going to turn out to be better. So let me quickly tell you a little bit, because it looks like we have time. Let me tell you a little bit about how this second pseudorandom generator works. So this is like a whole different topic. So if you didn't care for what happened before, this is totally different. This pseudorandom generator works a whole different way. So actually, the dependence on epsilon in our pseudorandom generator is so good that there's a simple reduction. We might as well forget that we're trying to fool AND of LTFs. We can just fool arbitrary functions of LTFs. It amounts to the same thing, actually. And that's the perspective we take. We don't even try to take advantage of the specific function AND. Let's just fool an arbitrary function of S LTFs. So the construction is a pseudorandom generator for multi-party communication protocols, or equivalently combinatorial rectangles. And there are a lot of standard pseudorandom generators. This is pretty well studied for this topic. And we don't actually need to use like the best pseudorandom generators for this model. It suffices for our purposes to just use something simple like Nissan pseudorandom generator for space-bounded computation, if you're familiar with that. So for the analysis, and this builds on prior work by Cabinets et al. The first step is this theorem by Nissan, and the parameters were improved by Viola, which says that an LTF can be computed by a k-party, for any k, can be computed by a k-party number in hand communication protocol using low communication. Okay. So if this were a deterministic communication protocol, then we would basically be done. We would say, well, look, if you can compute an LTF by a communication protocol, then you can compute a function of a few LTFs by just computing all those LTFs by their own communication protocols, and then we're done. But there is a difficulty here, which is that these protocols for the LTFs provably have to be randomized protocols, randomized communication protocols. Okay, and to get our seed length, we're going to consider randomized communication protocols with actually a constant failure probability. So the challenge for us is that we need to come up with some way of combining these communication protocols where this 1/3 failure probability is not going to translate into a high error of our pseudorandom generator. We want to avoid paying for that failure probability of the communication protocol in terms of the error of our pseudorandom generator. So the way we do that is, let's say we're trying to fool this function that's like g of a bunch of LTFs. G is just an arbitrary Boolean function. Then we use this really cool result by Scherstov that says polynomials can be made robust to noise. So Scherstov designed a low degree polynomial G sub robust, let's call it. This is like a multivariate real valued polynomial that computes G in a way that's robust to errors at the inputs. So for any input Z and for any error vector eta, if you introduce like additive error up to 1/3 at each coordinate, then the robust polynomial outputs the correct value to within this tiny additive error plus or minus epsilon. Okay, so this is a really cool theorem. I mean, I encourage you to read this paper if you're interested. It's very satisfying. So here's how that's useful to us. We have these communication protocols, one for each LTF. We have a separate communication protocol AI for each LTF phi. And they have, pretty good success probability. So if we let Qi be the acceptance probability of that protocol on input X, then we know that Qi is within additive error 1/3 of the correct answer, the correct value of this LTF. So Qi is the acceptance probability. So since Qi has this low error, then we can think of the Qi's as being like, all of these phi's, but with some noise. And we can plug those into this G robust function, this robust polynomial. And if we do that, this computes F with pointwise error epsilon. Okay. So that means that it suffices to fool this composition of this robust polynomial with these acceptance probabilities instead of trying to fool F, because we have this pointwise error epsilon. So to fool this polynomial, let's just consider a single monomial of the polynomial. So it's a product of these Qi's to some exponents, AIs. And it's a low degree polynomial, so the exponents, most of these are 0. They add up to some small value. Okay, so we'd like to fool now this function that's like Qi of X to the AI. And the way that we fool it is by interpreting it. That's the main step. We need to give some probabilistic interpretation to this quantity, multiplying a bunch of probabilities. Well, multiplying a bunch of probabilities has a natural interpretation, right? That's what happens when you look at the conjunction of a bunch of independent events. So we can design a protocol B to interpret this quantity, this product of the Qi's to the AIs. Okay, so this new protocol B says simulate the AIs a bunch of times independently. We simulate AI copies, little AI many copies of big AI. And then protocol B takes the and of all those answers. It accepts if all the simulations accept. That way, protocol B has acceptance probability exactly exactly this quantity that we're trying to fool. The acceptance probability of B is exactly product over I of Qi of X to the AI. Okay, and B is still a low communication protocol because after all, each AI used only a few bits of communication. And then the blow up here was like the degree of the polynomial, and Shurstov gave us a low degree polynomial. So since this is a low communication protocol, it's fooled by our pseudorandom generator. All right, so if we look at the expectation of this, this quantity that we're trying to fool, we can write that as the expectation of the acceptance probability of this B function, this B protocol, and then exchange the expectations. And now, and the inside here, this is exactly the sort of thing that our pseudorandom generator was designed for. It's designed to fool multi-party communication protocols. You can replace their inputs. Instead of using a truly random input, you can use a pseudorandom input and you get the same thing more or less. So that's how the analysis goes. There is one step that I've skipped here, which is that we only looked at a single monomial. We do also need to take into account these coefficients because they're going to blow up the error. The error is going to, these errors from the monomials are going to add up and get multiplied by the coefficients. But this just amounts to looking at the coefficients of Shurstov's construction, and it turns out to not be a problem. So that's our pseudorandom generator for polytopes. Now let me return to the LTF decision trees, which is what we really wanted to fool. Let me show you, there's a simple reduction. By fooling polytopes, we're also fooling these LTF decision trees, the simplified model that we had from the first part of the talk. That is, we're fooling LTF decision trees when they have individual LTFs at the leaves, so that the circuit depth has gone down to 1. The reason is you can take one of these LTF decision trees and expand it by summing over all leaves of the tree. And then you can look at the contribution from one leaf. So the contribution from one leaf of this tree is the indicator that says we reached that leaf times the LTF that labels that leaf. And this contribution from a single leaf is a polytope, right? What causes you to reach a leaf? It's if everything goes right on the path, everything goes correctly on that path to that leaf. So it's, a conjunction of a bunch of LTF conditions, because we have these LTF queries, don't forget. Okay, and so just by the triangle inequality and linearity of expectation, if we fool each of these terms, then we also fool the LTF decision tree as a whole. This is quite a large sum, right? We're summing over there are a lot of leaves of this decision tree, because remember, it's near maximal depth. And so that's why it was important that we fool polytopes with really, really small error, because that error is going to get blown up by this giant sum. But if you work out the parameters, it works and it stays non-trivial in the end. So that's the end of the second step. And I mean, that's the end of the sketch, at least, of the proof of this whole main theorem, that we get the first construction of a non-trivial pseudorandom generator for superlinear size LTF circuits. So let me just end with mentioning some directions for further research. I think one interesting problem would be to extend this to polynomial threshold function circuits, PTF circuits, low degree PTF circuits. I mean, you could see that much of the analysis didn't really rely on things that were specific to LTFs. A lot of it was pretty general. So I think this is probably doable. In the paper, we have another pseudorandom generator that we present using somewhat similar techniques for a different model of computation, though, for De Morgan formulas. And so once again, it uses like this sort of hybrid decision tree type of framework. And so I think this helps to showcase just how flexible and versatile this hybrid decision tree framework is. And it's probably a good idea to have it as a tool in your mind for pseudorandom generator problems and other types of problems. And I mean, we're not the first to notice this. There have been several prior works that use similar types of models, these hybrid decision tree type approaches, and it seems to be very useful. And so I think it would be great to develop it further and find more applications and further refinements of these techniques and approaches. Okay, so that's all I wanted to say, and I'm happy to take questions. Thanks for listening.
Hey, William, I have a question.
Yeah.
So does your results give new CAPP algorithms for this class?
Yeah, that's right. So the question was about CAPP algorithms, which just means like the non-black box problem, where you're given a circuit and you're supposed to estimate its acceptance probability. And so pseudorandom generators certainly immediately imply a way to estimate the acceptance probability of a circuit, namely just try all seeds of the pseudorandom generator. And yeah, there wasn't anything known before in this regime of parameters for these slightly superlinear size LTF circuits. So yeah, I mean, currently nobody knows how to take advantage of having non-black box access. There were some prior results, things like there was Rowie has some result about quantified de-randomization. So this is like where we're in this extreme regime of parameters where you get to assume that the circuit almost always outputs one particular value, right? And so Rowie does have results for that. And there were also some prior results for like the depth 2 case and stuff like that. But yeah, for the specific regime of parameters that we were fooling, yeah, this is the first non-trivial CAPP algorithm. Good question.
And one more question. So do you think these obstacles, maybe it can be used to explain why you cannot get a better worst case lower bound for this class?
Well, what obstacles exactly? You mean like the obstacles that showed up in the proof?
Yeah.
Yeah, I don't know. I mean, I hope it, you know, helps to elucidate a little bit what's going on, but I'm not sure how much it really gives a satisfying explanation. Because I mean, I wouldn't say it's totally clear, you know, why this barrier that showed up in our proof is like insurmountable. I mean, maybe we're just not clever enough, you know. I should mention though, there is sort of maybe a more satisfying explanation for why we're running into this wall at n to the 1 plus delta. There's some work, I forget now who the authors are, but there's a paper that says something to the effect of if you could prove slightly better lower bounds for TC0, like even if you could just improve the base of the exponent, where it's like, you know, this 2 to the minus d thing, if you could just improve the base of the exponent a little bit to something, you know, something a bit better, then those sorts of lower bounds can be like magnified, and they, you know, they imply some more exciting lower bounds. I forget exactly what. I'm not remembering any of the details of this result now, but there's something along those lines in the literature.
Okay, thanks.
Thanks, Williams, for this great talk. Can you mention the running time of your PRG? I'm not sure you mentioned it.
Yeah, good question. Yeah, you're right. I didn't mention it. All I said was
I think we lost your sound.
okay, sorry. Can you hear me? Somehow I messed up the microphone I was using, but this is just my laptop microphone.
Yeah, now we can hear you.
Okay, sorry about that. Yeah, so to answer your question, you're right. I didn't say specifically what the running time was. All we claim in the paper is just that it runs in polynomial time. I think with some modifications and optimizations, I think you could get it to be like strongly explicit in the sense that like each individual output bit can be computed in like, you know, slightly less than n time, like close to the seed length amount of time. But I mean, we haven't really carefully checked that. So.
Okay, so I'll stop the recording. We can stay hanging out. But thanks, Will, for the great talk. Here,
Yeah, thanks.